Good evening and thanks for joining us for tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at helping your students prepare for the AP Calculus upcoming exam this year with TI Technology specifically. So tonight we're going to be focusing on both the TI-84 and the TI-Nspire platforms. I see that many of you are joining us for the first time. So we'd like to offer a special welcome if this is your first T-Cubed Professional Development webinar. We'd also like to thank everyone for completing the live survey on the right side of your screen. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make those tough to teach, tough to learn concepts accessible to all my students. I'm really excited to introduce our two panelists tonight, Vicki Carter and Steve Kokoska. Vicki has been teaching high school math for 40 years and currently serves as the math department chairperson at West Florence High School. She is co-chair of the AP Calculus Development Committee and serves as a question leader at the AP Calculus Reading. Vicki has served on TI-Nspire authoring teams and has presented at many international, national, and regional conferences in the areas of technology, calculus, and statistics. Thanks so much for being with us, Vicki.
I'm glad to be here tonight.
And Steve received his undergraduate degree from Boston College and his master's and doctorate from the University of New Hampshire. Steve just completed his term as chief reader for the AP Calculus Reading and member of the Development Committee. Steve has written several graphing calculator manuals to accompany statistics and pre-calculus textbooks, and is also co-author of the CRC text, Standard Probability and Statistics Tables and Formulae. He has given numerous presentations on graphing calculators and AP Calculus at College Board workshops, the T-Cubed International Conference, AP National Conferences, NCTM, and to area high school students and teachers. The second edition of his introductory statistics text was published in January of 2015, and he is now working on an AP Calculus text. Thanks so much for being with us, Steve.
Mike, thank you very much. I'm delighted to be here.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send questions to Steve or Vicki using the Q&A window on the right section of your screen. Once we begin sharing our screens and our software, that right section of your screen will be replaced with a green floating toolbar at the top, and you can access the Q&A window by clicking the question icon. This session is being recorded, and as a reminder, we'll be providing a link to the event certificate of attendance at the conclusion of the webinar. There's going to be a few things that Steve and Vicki are going to be going through tonight that if you're trying to follow along on your handheld, I think it could really be kind of cumbersome and really slow you down. And so our intentions tonight are that you're not going to try and do this live with us, but you are going to hopefully wait for that recording, and that way you can go at your own pace and make sure you're entering everything correctly. We hope you don't have any audio issues tonight, but if you do, try selecting Communicate in the WebEx menu, choose Audio Broadcast, and click Join. At this point, Steve is going to discuss our agenda.
Thanks, Mike. You've already taken care of the welcome and the introductions. I'm going to begin by talking about the 4 basic calculator capabilities that are allowed on the AP Calculus exam. And what I'm going to try to do is to tie those capabilities with previously asked pre-response questions. And I'm going to talk a little bit about how to solve those questions with technology. I'll also talk about how they were graded, how they were scored on the exam. I'm going to show you some screen illustrations and discuss home screen calculations versus graph screen calculations. And at that point, after each of these capabilities, Vicki will probably chime in and show you a little bit more detail about how to get the calculator to solve some of these problems. My screenshots are generally the end results, but Vicki will show you a lot of the intermediate steps. She's much better at this than I am. Towards the end, we may talk a little bit about inappropriate use of technology on the exam. And if we have some time, Michael will show you some online resources. And perhaps the most important part of all this, there is a giveaway, which will be a complimentary registration for a T-Cube summer workshop, and Michael will take care of that.
Thanks so much, Steve. And Vicki is going to discuss our expected outcomes for tonight.
So tonight, what we hope to do is, by examining some recent AP Calculus AB free response questions and looking at it with the TI-84 and the TI-Nspire technology, that you will gain a better understanding of how you might use the technology to solve some of the problems that have been released. We will be looking at how to use the calculator both in graphing and analyzing the functions that we will show you from these questions, and we will use both the TI-84 and the TI-Nspire. Hopefully you will gain some knowledge about solving derivatives and integrals, which are important in calculus as we use the TI-84 and the TI-Nspire, and you will become a little more proficient with doing those skills on the calculator. And now I think we're ready for Steve to start our little presentation.
All righty. Let's see if this works. Hey, how about that? Is that working?
Looks good.
Okay, here we go. So the things that I'm going to talk about this evening are, I want to remark first of all about the 4 graphing calculator capabilities. I want to make sure that everyone understands those. And I just want to make a couple of comments about them. And then for each of those calculator capabilities or functions, I'm going to take a look at least a couple of previous AP Calculus free response questions. I'm going to look at the actual scoring standard just to make sure we know how it was graded. And then I'm going to show you the calculator solution. And after each one of those, I'll try to pass it over to Vicki so that she can show you more of the details. So the calculator use on the exams. As all of you know, both multiple choice and free response sections include problems that require the use of a graphing calculator. And these 4 capabilities have been around for probably over 20 years. And they are, of course, plot the graph of a function within an arbitrary viewing window, find the zeros of a function, but more generally, we want students to be able to solve equations numerically calculate the derivative of a function, and finally, numerically calculate the value of a definite integral. So once again, I'm going to try to hit all 4 of these and tie these together with AP free response questions and TI technology. Just a couple of remarks about all of this before we begin. Remember that there are quote-unquote calculator active questions on the AP exam, but that doesn't necessarily mean that a student will need their calculator. So there could be a question, there are often several questions that are calculator active, but a student can solve without the use of their machine. The 4 capabilities are the only calculator functions that a student can use to present a solution to a problem on the AP exam. Certainly, we want students to use other functions on their calculator. We encourage them to do so. Use any capability that your calculator has, but those are the only 4 that they can use to present a solution. Vicki and I both served on the development committee, and I can assure you that great care is taken when we write these questions to make sure that students using, say, for example, a CAS machine don't have any sort of an advantage. It's a very difficult thing to do if you've ever tried to write a question like this, but we want to make sure that no one has an advantage who has a CAS machine. And just as a little aside, there are some calculator issues I want you to know about that the development committee has kicked around over the last several years. One of them that's one of my pet peeves is it would be really nice, I think, to increase the number of acceptable capabilities. These 4 capabilities have been around for a long time. Calculators, technology has evolved tremendously. It seems like we ought to be able to allow the student to use more capabilities on the machine. It sounds easy to say that, but it's proven much more difficult to implement that. So for now, I think we're staying with the 4 capabilities. We all know that there is an equity issue among students. Some students who don't have access to the latest technology, to the best technology. That's a very difficult question to solve. We're not going to solve that this evening, but I want you to be aware of it. I want you to know the development committee thinks about that. And as you know, the number of calculator active questions, especially in the free response portion of the exam, it did change. It went from 3 to 2. And there was an awful lot of discussion about that in the AP Calculus community. Was there, did that signal a decrease of emphasis on technology? And the answer, of course, is no, it did not. I can't give you a real good reason why we did that, except that colleges, universities want to see students solve problems, solve calculus problems without technology. And it's very difficult. It has become increasingly difficult to write really good calculator active questions. And that's not a good excuse, but the number of calculator active questions did change from 3 to 2 a few years ago. I don't think there's going to be another change. Vicki, maybe you can address that later on. But I think we're going to remain at 2 calculator active questions in the free response portion. Okay, so I'm going to start by taking a look at the first capability, which is to draw an arbitrary graph or draw a graph in an arbitrary viewing window. And I had to go all the way back to 2002 to find a good example. And this one has to do with particle motion. We have a particle moving along the x-axis, and its velocity is given by that equation. And I'm focusing only in this question on part A. And in the exam booklet, we gave the students an axis, some axes, an x or a t and a v of t. And we asked them to sketch the graph for t between 0 and 16. So what you're seeing at the bottom of the screen is the actual scoring standard. There's a graph on the left-hand side. And this was worth only 1 point. And you can see sort of the 4 things that we were looking for when we graded this problem, the 3 quote-unquote humps. We wanted to see some sort of periodic behavior. We wanted the function, the graph, to start at the origin. And we hope that the students would give us some reasonable relative max and min values. So on the next page, this is the sort of thing that we would expect a student to do on the TI-84. So in the top left-hand corner, what I have done is I entered this expression, this velocity function, in the y equal menu. And then I went to the window and I set up the scales here, x min, x max. And you'll notice that I went a little bit farther. I went a little bit more to the left and the right. I went -1 to 17 so that I could see just a little bit more of the graph. I also chose an x scale of 4 so that that would agree with the tick marks that were given to me on the free response question. And on the y-axis, I went y min -8 to 8 and a y scale of 4, again, so that the tick marks would agree with what was given to me. And in the bottom left-hand corner of the screen, that's the graph that was produced by the TI-84, and that's pretty nice. And then the idea is that the student would be able to take a look at that graph and transfer that onto their test paper. On the TI-Nspire, what I did here, and Vicki will show you more of this, what I did was enter this function in a graph screen and set the window in a similar way. And there's a screen illustration of the graph produced by the TI-Nspire. That might be a little bit nicer. It looks kind of cool to me. I even get the expression for the function on the screen. And I think what I'm going to do now is pass this over to Vicki and let her show you a couple of actual keystrokes. So I'm going to stop sharing that. And Vicki, I'm going to try to send this over to you.
All right, so I think we just need to produce the graph on one of the calculators. So let's just look at the Nspire for right now. So I'll press the menu button, and I want to go to the graph screen. And I need to enter. Oh, no, hang on.
Okay.
I forgot that little minute detail. There we go. Now do you see it?
There we go. Got it.
Okay, good. All right, so here, I'll start over. So I'm going to open a new document, and I have a prompt as to what application I want to use. So I'll add graphs, and I want to enter the function. And students here, and one of the things I wanted to point out, some students who haven't had a lot of practice with the TI-Nspire might use the letter E instead of the number E, and they say, I can't get a graph. And I go, oh, well, maybe you used the wrong E. And so we have to talk about that in class, especially if this is sort of early in their use of the calculator. And then I had an exponent box already there for the exponential expression. So I'll type a 2, and then I'll find my sign function. Now, even though the particle is defined in terms of t, I must use an x. And again, I have a lot of students that will forget this and try to put a t into their graphing prompt that they have here for their function. And then the other thing that they forget is that the cursor is in the exponent, and we have a -1 that is not in the exponent. So they need to remember to press the right arrow bar and then there subtract 1. And if they press enter, they're going to get a graph that has more features than what we're looking for. So Steve was talking about finding an appropriate window that is similar to what the rectangular region that they had shown on the exam where they were supposed to sketch their graph. One of the ways to do that is through menu and the window zoom, which is number 4 here. So we could go to window zoom, and we could go to our window setting, and then we could put in our X-min, X-max, X-scale, Y-min, Y-max, Y-scale, which is fairly simple to do. I encourage my students to use the tab key as they go through the various lines in this box. So for instance, as Steve said, well, he gave it a little bit of a margin there, so -1, and then tab, and then a little bit of a margin, so 17, tab. The scale was 4, so I want to put 4, and then -8, tab, and +8, and again a scale of 4, and press OK. And now I have a graph that is very similar, or at least I can see the details that are very similar marks, like the 4 and the -4 and the tick marks, to what I would produce on the exam in the box that is provided. Now, one of the things that I have found out is that students don't like to go to that menu, window zoom, and window settings. They don't like to get to the change of the window settings that way. They have become very familiar with just double-clicking on the values, which are the Y-min, Y-max, X-min, X-max, and the tick marks, the scale. They can do it right there on the screen. So they'll actually edit it from here. So I'm just going to put something in that's not actually there. I'll put -4. And what they can do now is just press tab, and it will actually rotate around to the various values that they want to change, and they love doing that on their handheld. They think that's much easier. So I am now going to send it back to Steve.
Okay.
And let's look at a second problem.
Okay. Before I do so, I just wanted to make a couple of other comments about this graphing a function in an arbitrary window. I wanted to just take a quick look at 2005 AB4 because it's sort of a misconception here. If you take a look at this one, we have a table with FF prime and F double prime with various values and some features, some characteristics of those functions given. And I'm focusing in just on part B. It says on the axis provided, we want to sketch the graph of the function that has all those characteristics given in that table. Well, you know, someone might take a quick peek at this and think, well, this is a graphing calculator problem, and it is not. Some students, if they have their calculator in front of them, might try to put some values in for F and try to run a regression to get what this function would look like, and that's wrong. I just want to make that point. So this one, what the student is supposed to do is analytically take a look at that table, use all the characteristics given in that table, and produce a rough sketch of the graph. And that's what it's supposed to look like, taking into account where it is increasing or decreasing, taking into account concavity, taking into account whether or not the derivative exists. And that's the sort of a solution that we were looking for back in 2005. And there's one other feature that, or one other type of problem that I wanted to mention. Not one of the capabilities of the machine, but one of the nice things that the TI-Nspire can do. This is from 2014, a couple years ago, AB6. So in this one, in Part A, we have a portion of a slope field of the differential equation that's given up above. And the student is asked to sketch the solution curve that goes through the point 0, 1. And that's the kind of a curve that we were looking for from the student. And I can tell you, having been the chief reader for this one, we were very liberal in grading this one. But that's the kind of a curve we were looking for. The student didn't have their calculator for this problem. It's not a calculator active question. But if you take a look at this next page, I just wanted to make you aware that the TI-Nspire has some built-in capabilities that allow the student to produce this slope field very nicely, and also to produce the exact solution curve that we're looking for, a solution that goes through the point 0, 1. To the best of my knowledge, there's no built-in capability on the TI-84, but Vicki will have to help me on that one. But I do know that there are some programs available that will allow the student to construct some slope fields and maybe even some solution curves.
Yes, there are some TI-84 programs that will do that.
Good, okay. Thanks, Vicki. Okay, so the next capability that we want to take a look at is to be able to solve an arbitrary equation numerically. And for this one, I'm going to go to last year's problem, AB1, BC1, the rainwater problem. So we have a rate in and we have a rate out, and we're looking between 0 and 8. And in Part C, we're asking the student, look at what time t in that interval, at what time is the amount of water in the pipe the minimum. And we're asking the student to justify their answer. This is what the solution looked like on the standard for Part C. It was a 3-point problem. You'll notice the first point here is what I would call sort of a conceptual point, or want the student to convey to us that they know to consider R of t minus d of t equal to 0. The second point is for the answer. They're actually telling us when the amount of water in the pipe is a minimum. And the third point is justification. And justification in this problem could be, in fact, that table of values. That's justification that we know where the minimum occurs. There are certainly other ways to solve this problem. That happens to be the style that I tended to like, presenting a table of values here. All right, so how does the student use their calculator to solve this problem? Primarily here to set R of t minus d of t equal to 0 to solve the equation where R of t equals d of t. And so here are several screenshots from the TI-84. I'm just going to comment, and Vicki will add a couple of things too. I wanted to comment on solving this problem on the graph screen versus the home screen. It's always been my mantra that we should allow the students to explore the solution on the graph screen, but always confirm that on the home screen. Vicki and I think, are in agreement that for finding the intersection point, we're pretty confident that you'll always get the same answer on the graph screen as you do on the home screen. But I'm still a little uneasy about that, and I would always confirm that on the home screen. So here's what I did up in the top row. I entered those two functions, R of t and d of t, in the y equal menu. Just to show you what this looks like on the graph screen, I plotted both of those in an appropriate window, and I used the intersection command to find that point of intersection. Down in the bottom row, I solved this problem on the home screen using the numeric solver. And in that window, I would enter the two functions, y1 and y2, or in this case, what I want to do is set y1 equal to y2 and solve that expression. And what I generally do is I give the calculator sort of a starting point and a bound to look, in this case, between 0 and 8. And just to go a little bit further, you'll notice in the bottom right-hand corner, as the calculator found that point of intersection, I stored that in a value or in a variable A, and I was actually able to use that variable, use that expression, use that solution to find that actual minimum value at 27.9646. And here I did a little bit of that with the TI-Nspire, working on the home screen on the left-hand side. I entered the functions R of X and D of X. And Vicki and I have been talking about this. What I initially used was the solve command, which in my mind is it starts out to try to analytically solve that equation. And I asked the calculator to solve that equation over the interval 0 to 8, and it came back, of course, with 2 solutions. You'll notice that there's a little yellow warning box over there, which is an indication that, you know what, there may be some other solutions that the calculator was unable to find. On the right-hand side, I have a solution on the graph screen on the TI-Nspire, and thankfully I'm still always finding that 3.272 for the x-coordinate. And what I wanted to be able to do on the TI-Nspire was I wanted to be able to solve, to save that solution to that equation, to use it later on. And this was one way that I did it, and I think Vicki will show you a couple of others. I actually said set t equal to that numerical solution. So now I'm using nsolve versus solve. And in the second line on that screen, I just typed in a t just to make sure that I did indeed get it. Remember that that is stored to a much higher degree of accuracy in the background in the calculator, but I have it displayed here to 5 decimal places. And then I use that value of t again in order to find that minimum value, that 27.9646. So I'm going to show you one more, and then I will pass this over to Vicki. This was also on the 2015 exam. This was on the BC portion of the exam, but a very easy one, and I think a very good example. This one also had to do with particle motion. And in this problem in part B, we told the students that there is a point on the curve at which the line tangent to the curve has slope 2, and we wanted to know the time at which that object is at that point. So at the bottom of this page is the solution from the standard. This was worth 2 points. And we asked the student here to show us dy dx and set that equal to 2. I think this is a good point to remind everyone that when the student is using their calculator, they must still tell us the mathematical equation that led to that solution. So they need to tell us that that quotient is equal to 2 and that that's the equation they're solving. And there's the answer there, 0.840. So on the graph screen on the left-hand side here, what I did was I entered that quotient, and I graphed the quotient that's in blue, and I graphed the line y equal 2, and I found the intersection. And on the right-hand side on the home screen, again using the numeric solver, I took that quotient and set it equal to 2 and solved, and asked the calculator to find me a solution between 0 and 1. And again, thankfully, it came up with the exact same value. Here it is on the TI-Nspire, looking pretty nice on the left-hand side on the graph screen. Again, I have the equations for those 2 graphs, and I used the intersection feature on the graph screen to find that value of that x-coordinate, or okay, the t-coordinate here. And on the right-hand side on the home screen, again, I used the numerical solver to find that value of t. So again, we would expect that the student would tell us the mathematical equation that they're solving, but then go to their calculator, and I would advocate solving that on the home screen. Okay, I'm going to give this back to Vicki, and she'll show you a couple of the calculator steps. I'll pass that over to you. There you are, Vicki.
Okay. So we had a question about the showing the slope field. So I think I'm just going to show you a little bit about it. I'm not going to get into a lot of details, but give you an idea of how you could start exploring this. And I find it very beneficial that when I'm teaching slope fields for the students to just look at a lot of different solution curves over a slope field, because it gives them a better idea of how they would have to draw one in a given slope field through a specific point. So first of all, you need to open a graphing application. You're going to go to Menu and go to your Graph Entry Edit line, and you'll notice a lot of features there. Function, which is the default, but if you'll look at the very bottom, there's differential equations, and that's essentially what we're doing. So we'll pick differential equations, and if you look very carefully, it's kind of tiny, but it says y1, and that's a little prime. So y1 prime is the actual derivative that we will be typing in. Now, in this case, it's y1 prime. So when I have the slope field that was actually given in that problem, of course, they don't have a calculator during this time. So this is an experience they need to have during the class when you're teaching this particular topic. So I'm going to put my parenthesis and my 3 minus, and I can't just stop with a y because it is specifically referenced to y1. So I need to put y1, then close my parenthesis. I need to put my multiplication, and then my trig is cosine, and again, it's of y, so it's of x, so I don't need to worry about that. So of x, and if I put this in and I hit enter, I get a slope field. It's not as attractive as the one that was on the paper that they were drawing their slope field through. Of course, I can adjust my window like we did a few minutes ago, and we might see a few more. It may look a little more like what we have. So I tend to be very careful about the ones that I actually pick out that we would use. I'm going to change the window very quickly to see if it looks a little bit better. And so you can begin to see the pattern that was in the computer-generated slope field there. If I press Tab and go back up to y1 prime, you'll notice that in the second line it says x0, y1 naught. I can actually put in an initial condition, and in this case it was 0, 1, and hit enter, and I have that solution curve. One other thing that I want to mention about this that a lot of people don't realize is that with the 3 little dots here with the parameters, so I'm going to click on it. It by default is in Euler's method as far as the solution method. You may want to go to Runge-Kutta for displaying these slope fields. They look a little smoother sometimes, and I mean that's just something you may want to consider. Oops. And so we have this, and that's how you can have the kids just practice seeing some various solutions to slope fields, and you can actually just take that initial condition and move it, and so that they could see other variations. And I just think that's really important as an exploration for the students when they're studying slope fields. Steve, what else do I need to show them? Do we want to go look at a little bit with those 2 problems that you had?
Your choice. If you want to show how to solve that on the home screen,
okay.
That would be great.
All right, so these were the 2 rates that were given in the 2005 AB1. And we want to find where they intersect. So I could possibly go to a graphing screen. All right, and this is just something that I do in my classroom. I tell the students to define it in terms of the variable that we're actually using, so we define it in terms of t. But if they want to graph it, so when I add my graphing screen, it's very easy. They don't have to retype it, so they can just put, so if one of them was r of t, so we can just put r of x and down arrow, and the other one was d of x. And so I'm just changing the variable there, and so I get the 2 curves. I'm sorry, I'd already graphed something, so we get this nice, lovely hot pink and black. And so if finding the points of intersection, so they could do menu and then analyze graphs and intersection, and it asks for a lower bound, so I won't, and of course I know that that one's 0, 0, so we're going to look for this other one, so we could do a lower bound. That means we need to be to the left of the intersection point, and then an upper bound we need to be to the right of the intersection point. And one of the things that happens very frequently when you solve on the graphing screen is that you only have 2 decimal places displayed. There's several options here. The students can hover over the value that they need to see more decimal places for, and they can press the plus key, and it will expand that. I typically tell my students to press the variable key, and we're going to store it. And so I might store it as A, and when I hit enter, notice that that x-coordinate is now bold, which means it's stored, and if you hover over it, it says it's linked to the variable A. If I go back to my calculator screen and just type A and enter, I will see that value that's an intersection point, and then of course if I hover over it and copy it, then I'll have more decimal places. We'll get the same thing if we do the manual solve. So if we do menu, algebra, or we could do a numeric solve, which is also important that they kind of see some different ways. So numeric solve is what the TI-Nspire CX, that's the numeric, and the TI-84 actually has a numeric solve. But we'll do the solve here. So I need R of T equal to D of T. I need to tell the calculator that I want to solve for T. And one of the things that the students need to become very familiar with is, especially when they're working with the trig function, they need to restrict the solutions that they're going to see. And the way that they do that is with control equals, and we want the such that. And then they can type in 0 is less than or equal to T is less than or equal to, I think it was 8. And when I hit enter, I'll get the 2 solutions, which are 0 and 3.27166. And Steve and I talked about this and about how it might be an efficient way to solve, to store that 3.27166 from this screen. So what I tell my students to do is to go up and highlight it, press enter, and then it's pretty easy on both the calculator, and of course I'm using a computer, which is a little bit easier, but it's pretty easy on the calculator. Just go to the front of the number and delete the stuff you don't want. Come back to the end of the decimal number, the numeral that you have here. Press control variable, which is store, and now you can store it to, well, just like an L, and hit enter. And you see that we have the same values essentially, and I went up and highlighted and pressed enter. So I'm getting the same values that I got from the graphing screen and the calculator screen as far as the point of intersection. Steve, let's look at another problem. I got a few more of your problems, or if anybody has anything in the chat that they want to talk about, we can do that. So I'm going to pass it back to you.
Okay.
All right, here it goes.
All right, here we go. Beautiful. Okay. All right, so how about this, Vicki? How about if I take a look quickly at these last 2 capabilities, and then I'll pass it over to you.
Okay.
So the next one is we need to be able to numerically calculate the derivative of a function. So this one I'm going to look at 2014 AB1 BC1. This one had to do with the famous grass clippings problem. We have this function A of T, and we'd like to find in part B the value of A prime of T. I'm not worried right now about interpreting the meaning of that value, but just using the calculator to find A prime of 15. And if you take a look down in part D, we're looking at a linear approximation, but part of that problem was also to find A prime of 30. So a very similar sort of a problem, finding a numerical derivative. So I did this on both the 84 again and the Nspire, and here I am on the 84 on the home screen on the left-hand side. I kind of like that pretty print. I had entered that function A as Y1, and I found the derivative at x equal to 15, and there it is on the home screen. That, again, is my preferred method. Just as sort of a confirmation or exploration, I did it on the graph screen also. I sketched a of t, and there is an option there to find a numerical derivative. I'm a little uneasy about using that as my final answer. I would always take the answer that's on the home screen. On the Nspire, there once again I have it on the home screen on the left-hand side and the graph screen on the right-hand side. The notation or the display on the Nspire is really kind of stunning. It's very nice mathematically. The derivative of a at t equal to 15, and thankfully, again, the same answer. Whoops. So in the last one, what we need to do, the last capability is to estimate the value of a definite integral, and I'll go back to this one, 2015-82. This was kind of a cool problem. Students actually solved this in a way that we didn't think about earlier when we were writing the standard, and I'll try to have the opportunity to show you that one. We have these two functions, f and g. They define two regions, R and S, and in part A, we want the sum of those two regions. In part B, we have a volume of a solid that we're interested in. We want the students to find that volume. And even in part C, while we're here, darn it, we want the students to consider the vertical distance between those two graphs and find the rate at which h changes with respect to x at a specific point, 1.8. Here's the standard for this problem. In part A, 4 points, 1 point for the limit, 2 for the integrands, and 1 for the final answer. Again, the student would have to use their calculator to get this answer. In part B, 3 points, 2 for the integrand, and 1 for the final answer. And down there in part C, there's a conceptual point down there. We wanted the student to convey to us that they are considering h prime appropriately, and then finally giving us an answer, a numerical derivative. So here's a couple of solutions to this using the technology. I did a little bit of exploring on the graph screen up in the top left-hand side on the TI-84. I found that point of intersection. I went back to the home screen, double-checked. There's my point of intersection on the right-hand side at the bottom. I stored that point of intersection in the variable a. And then what I did, I guess kind of naively here, as the way I would teach my students to do this, is I found that definite integral from 0 to a. I recognized what the high curve was, what the low curve was. I found the appropriate definite integral, and I stored that in another variable c. And again, I understand that you can do this all in one step. I mean, my style is to try to parse these out so that I can see each step. In the next one, I found the definite integral from a to 2 of the appropriate difference and stored that in D. And then finally, I added those two values together for the final area of those two regions. Here it is on the TI-Nspire graph screen, a really nice picture, really nice illustration of those two graphs. There's the point of intersection. And here I did a little bit of that on the home screen on the TI-Nspire. So I entered and defined the two functions f and g, found the point of intersection in that third step. And just for the heck of it, I found the y-coordinate of that point of intersection. I don't think I needed that in this problem, but I found it anyway. And then on the right-hand side, I have the definite integral from 0 to a. And again, I stored that in a little bit different style using the store key on the TI-Nspire. Found the second definite integral, and then added the two together.
Hey, Steve.
Yes.
Never mind. I think you might just be answering that right now. Sorry.
Okay. And there was an alternate way to solve this one. We didn't think that students would do this, but in fact, it worked very nicely. Students could actually take a definite integral of the absolute value of the difference of these two functions without finding the point of intersection. And that was perfectly acceptable and received full credit for this. So on the left-hand side, I did this with the TI-84, and I just wanted to show you that on the right-hand side, I initially did this as a definite integral with the Nspire, and it would not give me an answer. And I believe the reason for that is because it tried to find an analytic expression for the integral. It could not do that, and so the way that I had to do this on the Nspire was with numerical integration. And that sort of begs this question, too, is what happens if the student tries to solve this problem analytically, actually tries to integrate this, come up with an answer? Well, they can't do that. And as long as the student sort of abandons that work and goes back to the calculator, we're willing to ignore any incorrect work there. At least we've done that in the past. And finally, over here for parts B and C, there's a definite integral for finding the volume of that solid. And on the right-hand side, there's the answer to part C. I found the two numerical derivatives. Again, my style is to do this in steps. And I took I minus j to find the actual derivative of h at 1.8. And there I did parts B and C on the TI-Nspire. Again, I got a warning when I did that definite integral, but I still got the answer. I felt a little uneasy about that, and so I did it with the numerical integration command and got the same answer. And on the right-hand side, there's my step-by-step solution, my parsed solution for part C. And I will hand it over to Vicki.
Well, hang on just a minute before you.
Yeah. Go ahead.
I've got it. I can do it. It's not a problem.
Okay, there you go. What do you want to look at?
All right, I want you to go back a screen or two. I don't remember which one it is. Go back to, it's a graphing screen. There. One of the big issues that we had with the students on this particular problem is that they eyeballed the intersection point as 1. And so you need to tell students to make sure that they calculate that intersection point, not just look at it and say, oh, that looks like 1, and I'm going to use 1. And so that's really important that they realize there are some calculator tools they need to utilize as they answer these questions.
Okay, should I hand it over to you?
Yeah, you can hand it over to me.
Okay. There you go.
All righty. Okay, now I'm not real sure what are some of the different things. I've been kind of looking at the questions and all. I'm not sure what you actually need to see at this point. So I can look at the chat, but I did have a couple of things that I wanted to mention that I think I'll run through. And if we need to show you something, we can do that. So this is a question from 2011. It is a question that I actually served on the question team for, and I'm only going to look at part D and only part of that question. But in this case, the students were given the temperature of some biscuits. This was the tea and biscuits question from 2011, AB2, BC2. And they, of course, they already had done some problems with the tea part of it, but then in part D, we introduced some biscuits, so this became fondly known as the tea and biscuits question. But the biscuits had a temperature of 100 degrees when they were removed from the oven, and the temperature of the biscuits at time t is modeled by differentiable function b, for which it is known that b prime of t equals, and then we gave them this exponential function. One of the things that we ran into is that we wanted, obviously, students to use this idea of this initial value plus the definite integral of the rate from t equals 0 to t equals 10, which is the way that the solution is actually modeled. And then they had to do a little thing about the difference between the temperature of the biscuits and the tea. But it's actually this part of the definite integral that I want to talk about. A student should never on this AP exam have to calculate an indefinite integral. If they're trying to do an indefinite integral, they're essentially doing it wrong. We did learn then, and when we found what students were doing with this problem, is that they were trying to do the indefinite integral, but if you've done this with your calculators, you know it doesn't give you a plus c, so they didn't have a constant of integration, so they would just take that function, evaluate it at 10. Of course, they had the wrong answer. So most of the time now you're going to see problems that are basically impossible to find an indefinite integral for, such as the integral of sine of t squared dt, things like this. So often on the listserv I see teachers asking questions about, you know, I can't get the antiderivative. Well, you shouldn't be getting an antiderivative for that. Another one is, well, this is actually a case in 2013 AB2 where we did give a velocity function where you're not going to be able to take that antiderivative. One of the things that came up in this one is in part A, where we find all values of t in the interval from t from between 2 and 4. 2 is less than or equal to t is less than or equal to 4, for which the speed of the particle is 2. Most students found when the velocity of the particle is 2, not the speed. And this was really nice to set up as either the graph of the absolute value of the given v of t that we had, or to actually graph v of t and remember that you need to look at like y equals 2 and y equals -2 and find both of those intersection points. So just vocabulary and making sure they're doing the right thing on the calculator. So this is another example of when they would not really, they do not need to use an indefinite integral. This is, the intention is totally for a definite integral here as they find the position of the particle at a time t equals 5 when we had given them the position of the particle at t equals 0. I know I'm going a little bit fast here, but I'm trying to make a point about students not doing indefinite integrals on their calculators during the exam. So I just had a few things that I wanted to say that were like problems. Very often when they're using the calculators, they forget to report their values to 3 decimal places, but they need to retain the saved value in the calculator and use the saved value, not the 3 decimal place reported value. The second one I mentioned just a minute ago, not to use the trace feature to find points of intersections or 0. Another one that we occasionally see, it's not as bad as it used to be, but they do not, they cannot use calculator syntax to tell us how they're going to do a problem, like the function numeric integrator command that we used to have on the older calculators. They do not need to use the expression with the capital E in it that's a scientific notation as a result of some calculation. And again, they do not ever have to find an indefinite integral with a CAS handheld. So if they're trying to do that, there's a way to do the problem with a definite integral. I'm going to stop sharing my screen so we can see what questions we have. Mike, do you want me to pass it to you or back to Steve? What do we want to do at this point?
Steve, if you don't have anything else, we could probably pass it back to me.
Okay.
Yep, back to you is fine. Yep.
As I was looking at some of the stuff that Steve presented, just one thing popped into my head, and Steve and Vicki, you can either agree or disagree. In the past, I remembered very few problems, but nonetheless, a few problems that were free response, where I think, Steve, earlier you were showing an area where you had stored a value that had, you know, a nice long string of decimal point values. And so instead of reusing that and recopying that long string of values down, as Vicki said, to at least 3 decimal places of accuracy, is it okay for students to write on their free response test, define K equals whatever that string is, and then on their free response test, the AP reader will actually, they can use K throughout the rest of that calculation, and they're okay with that?
Absolutely. As a matter of fact, we prefer that.
we encourage that, yes, absolutely.
Yeah, a lot of my students will just be working really, really fast, and they'll make copy errors and things like that, just from the speed at which they're trying to work, I think, and not paying attention. Sometimes those decimals can really take them for a spin. So as we do wrap up things tonight, if you have any last-minute questions for Steve or Vicki, please feel free to get those asked. I know they'll do their best to get them answered. In case you are either new to some of the technology that you saw tonight or looking for some refresher on that technology, I'm going to share some resources available on our website, which is education.ti.com. And if you move under the Professional Development tab, there's a choice that says Webinars and Tutorials. And so if you like what you saw tonight, feel free to check out the live webinars. For any additional webinars that are coming up this spring, we do have a few. We're excited about the upcoming webinars that are remaining this spring. We're duly excited about the on-demand webinars. Those are all the webinars that we've ever had. They've all been recorded. So if you're looking for other webinars that are, say, specific to AP Calculus, you can search the on-demand webinars for calculus-specific webinars and see what we've done in the past. As I mentioned, the far right there is technology tutorials. And say you're a new user to TI-Nspire, you're looking for more information. Our friends over at Atomic Learning have created short videos for all TI-Nspire products, the TI-Nspire handheld for computer software, as well as the TI-Nspire app for iPad. And if you are looking for a brush up on some TI-84 tutorials, you can click on the graphing tutorials at the very top, and then you'll see there's Atomic Learning tutorials for the TI-84 Plus C, as well as the TI-84 Plus. So please feel free to visit our website to get some more online resources. When you leave the webinar, a brief survey will automatically appear in your browser. I think Steve and Vicki did a great job tonight, and I'm really excited for all the information they were able to share. If there's things that you wish you would have seen or would like to see, please feel free to let us know. Those are all things that we can take into consideration for future webinars. We definitely listen to your feedback, and we truly hope you'll share your thoughts in the post-webinar survey. Earlier, Steve mentioned that tonight we'll be giving away a free registration for a T-Cube summer workshop. Our summer workshops are amazing. There's probably, I think, about 50 or so, maybe a little bit over 50 being offered this year in different areas, whether it's specific to a technology. Maybe you're looking, again, to brush up your TI-84 skills or your TI-Nspire skills or specific content. So if you're looking for more calculus specific or maybe something in statistics, you're going to be teaching statistics for the first time next year and you want to brush up on some of that content, or pedagogy. All three of those are going to be offered in different areas in the United States across this summer. So please feel free to visit our website and learn more. And again, as I mentioned, tonight we're giving away one free registration. And tonight's lucky winner is Melissa Brown. So Melissa, congratulations. We really hope you will take advantage of that, and we'll see you this summer at a T-Cube summer workshop. And we'll also be in touch over the next couple days over email to give you more information. Feel free to continue the conversation that you guys have already started tonight in the chat window and the Q&A window on any of the major social media outlets. To receive a certificate of attendance, please click the link in the, there we go, chat window. Also, this is the link for the documents tonight. So for example, the PowerPoint that Steve and Vicki used to share a lot of their content tonight is listed in that documents that I'm sharing with you tonight. So please feel free to download that. If you happen to miss it for one reason or another, you'll automatically get a follow-up email within a couple of days that will have a link to the recording as well as a link to the certificate and the documents as well. And if you happen to be watching this in the future on demand and you would like a certificate, go ahead and just write down the link and type that into your favorite browser. We hope we were able to answer all of your questions tonight, but if we didn't and you're looking for more follow-up, please feel free to either give us a call or send us an email. Thanks so much, Vicki and Steve, for sharing everything tonight. I know I had a good time, and I hope that you did as well.
Thanks, Michael. Great job.
Thank you, everyone.
Thanks again. We hope to see you back online next week. Have a great night.